Okay, so we can look at how this difference in temperature ends up manifesting itself in terms of the winds as a function of height. So again, we have this profile here where we have cold air over the pole, warm air here over the subtropics. We start off with initially the same surface pressure, and we look at the elevation of the different pressure surfaces with height. And so what we see here is that the slope increases as we go further and further up, and this is just due to the accumulation effect of warmer air over the subtropics versus the poles. And the pressure gradient force, of course, is then related to the slope of this line, and what you see is that that pressure gradient force will continue to increase as we go higher and higher up into the atmosphere. That becomes important because that tells us essentially that we're going to get stronger westerly winds aloft generally because we have warmer air in the tropics and colder air near the poles. And this is just using that geostrophic balance relationship. So let's take a couple steps together here and try to understand what this is going to mean for atmospheric circulation. We started off with the one-dimensional model of the atmosphere, and now we've added in the fact that we have a rotating planet. And so the thing that we have to think about is what that is going to mean in terms of circulation. So we'll think about a parcel which is released at the ITCZ, rises up with the ITCZ released near the equator, and we're wondering what's going to happen as it moves poleward. So the question here is what will be the final speed of this parcel if it's released at the top of the ITCZ? And we know that the upward branch of the ITCZ moves poleward, so the parcel should move poleward as well. But because we have to contend with the Coriolis force, the parcel will probably be moving at a very different relative speed at 60 degrees north versus the equator. We'll assume at the equator that the relative speed was zero. There was no momentum. It was just started at 0 meters per second relative to the rotational rate of the planet. Right, but the rotational the velocity of the solid Earth at the equator is far greater than at 60 degrees north. And if we are to conserve angular momentum, that is going to result in extremely strong winds, extremely strong winds by the time this parcel reaches the mid latitudes. So, as a refresher here, the solid Earth rotation at the equator 465 meters per second. Okay, and by the time that parcel, which is initially moving at a relative velocity of 0 meters per second, by the time it gets to 30 degrees north latitude, it's going to be moving at 134 meters per second and 435 at the pole. And that's a problem because observations show us that the subtropical jet, so the observed wind speeds, at least in an average sense, are only around 35 meters per second. So there is a question in terms of where all this momentum went. So we're violating some laws of physics here, and therefore this model is going to have to be tossed out. We're going to have to find another way to explain what is going on. And the answer to this is that we actually have a three-cell model. We have two thermally direct circulations, one being the Hadley cell. We've talked about that. We have a polar cell, which looks very much like the Hadley cell. It's doing the same job. It's taking heat energy from regions of relative energy surplus. In this case, it's areas of less deficit, which is near the subpolar region, 60 degrees north, and moving that to high latitudes where there is a maximum energy deficit. So this is thermally direct. In mid-latitudes, there is something very different going on, and that's in the realm of atmospheric waves. So that's a different topic we'll get to later. The three-cell model also allows us to explain what happens to all that momentum. So Polly the parcel, right, back to her story. She started in the tropics, moved up with the ITCC, started to move poleward, started to acquire a lot of western, started to move eastward because of the solid angular momentum conservation. And that momentum ends up actually being fluxed downward and to the surface. And this explains where all this momentum is going. And it ends up that if you look at winds, surface winds in mid latitudes, they tend to be westerlies. And what's actually happening there is that the atmosphere is actually moving faster than the solid Earth. So um, it turns out that the atmosphere is actually helping to push the solid Earth faster, whereas the opposite's happening near the tropics. In the tropics, we have easterly winds, and the that is actually acting to oppose the Earth. So we have that's where the momentum flux comes into play. So the three cells that we have to contend with, there is the Hadley cell, the polar cell, and then also in mid-latitudes we have a thermally indirect Ferrel cell, which ends up being an outdated term. That both the Hadley cell and the polar cell do their job, and they do it well. They act to um, take energy from regions of relative surplus and remove energy, take energy from regions of surplus and move it to areas of relative deficit. Um, Whereas the Ferrel cell does very much the opposite, and it ends up being superseded by eddies and waves in the atmosphere. So let's talk about the surface circulation arising due to this three-cell model. We'll first start talking about the subtropical highs. This is where we have the descending branch of the Hadley circulation. We have subsiding air, we have high pressure, we have a lack of cloud cover. This is perfect for developing areas of the desert areas on our planet. And it turns out that most of the desert regions on our planet tend to be associated with the descending branch of the Hadley circulation. So assuming we have a surface high pressure in the subtropics, we're going to have flow out of that high both to the north and to the south. South of that subtropical high, we're going to have flow from high to the intertropical convergence zone towards the low, and then we have that curvature to the right. So we end up developing these trade winds, which are moving equatorward and also westward. So trade winds are an important attribute there. North of the subtropical high here, we have flow from high to the subpolar low. So again, we end up developing flow to the north, and then it curves to the right, and surface westerlies arise due to that. At the equator, we have this zone that we call the intertropical convergence zone. From both hemispheres, we have air that converges here, and we also have an area where we have a lot of additional heat that is being entered into the system. So we have a net surplus, maybe a maximum in net radiation balance going on here. Very warm air. Air is rising. It's also converging, and so we end up developing quite a bit of cloud cover in the ITCZ. It turns out that it's somewhat challenging to usually see the ITCZ. It's not well defined across the entire globe. It tends to be actually more well defined in areas of cooler sea surface temperature. Areas of higher sea surface temperature tend to give way to larger scale convective systems, not this sort of linear type feature which we think of as the ITCZ. In high latitudes, we also develop easterly flow. Again, we have a high over the pole, and we have a subpolar low just south of that. So again, air flows from high to low. We develop easterly flow, northeasterly flow in general. And again, we have subsidence over the polar high. And in the subtropics directly, so this is directly in the area where we have the subtropical high, we end up actually getting relatively calm conditions, calm winds, and again, like I mentioned earlier, clear skies. These are areas to a lot of the deserts of the world. And because we generally develop very, very calm winds in these areas, they have been traditionally known as the horse latitudes. The reason being is that in the era where we had cross-sea voyages via ship, going from say Europe to North America, you always wanted to be south of the subtropical high so that when you're sailing, you could be pushed along by the trade winds. But if you happen to find yourself in the subtropical high, the winds were weak, you actually could stall out for a number of days, and depending on food supply, those horses might actually look pretty tasty, hence horse latitudes, or the story goes that way.